In this video, I'm going to prove the Cayley's theorem that the number of spanning trees in a complete graph of size n is equal to n to the power of n minus 2 by score. So what's the score? Let's see. You know, when I have n vertices and I have a tree on n vertices, then the number of edges is equal to n minus 1. And by handshaking lemma, we know that sigma of degrees is equal to 2 times the size of the set of edges, which means that the sigma of degrees of the spanning tree is equal to 2 times n minus 1, which is 2n minus 2. So we have a sequence of degrees, right? Each of those nodes, 1 to n, has a degree. So I have this sequence, and I know these degrees are all greater than 0 because I cannot have a degree of 0 in a tree, right? Because it is a connected graph. So I know all of these numbers are greater than 0. And also I know the summation of the I is equal to 2n minus 2. Okay, one result now. I have n numbers. All of these n numbers are positive integers, and the summation of them is equal to 2n minus 2. From this, I can realize that at least one of these numbers is equal to 1. So I can say there exists, like, let's say, for example, m, such that the degree of vertex m is equal to 1. Why is it true? Because let's say there is no degree of 1. So everything must be greater or equal to 2, right? So if all of these are greater or equal to 2, the summation becomes greater or equal to 2n, right? So it is not possible that all of these degrees are greater than 1. At least one of them must be equal to 1. Actually, I can say something stronger, but let's keep that. And let's say that at least one of these degrees is equal to 1. Actually, it makes a lot of sense because I have a tree, right? And in a tree, for sure, I have a leaf. So it is kind of obvious if you see that from that perspective. Okay, so here I want to prove something, a proposition, and in my proposition I am going to use all the information I already stated. So the proposition say that if I have a degree like d1, d2 to dn, and I know the summation is equal to 2n minus 2. I know all of them are positive integers, and it is 1 degree sequence of a spanning tree, then there will be n minus 2 factorial over d1 minus 1 factorial, d2 minus 1 factorial, all the way to dn minus 1 factorial. I want to prove this statement. Let me write the proposition here. You already have the document, but also I'm going to state that in a precise way. The number of spanning trees of the graph Kn in which the vertex I has degree di. For I1 to n is equal to the formula we have here. It is equal to n minus 2 factorial over d1 minus 1 factorial all the way to dn minus 1 factorial. Actually, we know that those n positive integers are creating that degree sequence. Okay, let's prove this proposition. So it is a proposition, and you know this number is for that special degree sequence, like that d1 to dn. So for another degree sequence, we have again this number for that degree sequence that we are going to take care of that and find the summation later. Okay, I'm going to prove that proposition with by induction. Actually, we see that when I have only n is equal to 1, I don't need that proposition, and I can say that there is only one spanning tree for the complete graph of size 1, and for complete graph of size 2, this formula will give me 1, which is again really obvious. So I'm done with my base case actually, and I'm going to start my proof for some n greater than 2. And actually it is like I assume in my induction hypothesis that the statement is true for k n minus 1. So for a complete graph of size n minus 1, we believe that the statement is correct. So for n minus 1, it will be n minus 3 factorial over that sequence with like n minus 1 degrees. So here for n greater than 2, what I want to do is okay, I have the degree sequence as mentioned before of d1, d2 to dn, and we're sure that at least one of them is equal to 1. We know at least one of the i's is equal to 1. Okay, you see, if I have that degree 1, I can say, okay, let's say it is my n node, okay? So what I want to do is that without loss of generality, I assume dn is equal to 1. And let's see what happens next. That the n can be connected to any other vertices, right? Because since the n is equal to 1, it means that it is a leaf. And when it is a leaf, it is connected to something else. It can be d1, d2 to dn minus 1. So I call this the vertex j, okay? And I want to define a family Tj as a family of trees such that dn is connected to vertex j. So it is different family of T1 is the ones that dn is connected to vertex 1. Family T2 is the ones that dn is connected to vertex 2. And until I have the vertex n minus 1, and I say that n, actually vertex n, sorry that I always talk about that as dn. dn means that degree of n. So that vertex n is connected to n minus 1. Okay, so defining that Tj is the family of trees in which vertex n with a degree equal to 1 is connected to vertex j. And now let's see what happens if I disconnect that dn with its edge, the attached edge, because it has only one edge, right? So if I do that, what happens? Then I have a tree on n minus 1 nodes, right? And I can say that it is a spanning tree for a complete graph of size n minus 1. So you see, for each of these Tj's that I have a tree of size n such that the n is connected to 1 or 2 or 3, it's like I have a spanning tree with the degree sequence the same as this, but dj minus 1 and no dn because dn is removed for k n minus 1. So Tj prime is the family of trees with degree sequence d1, d2, dj minus 1, dj minus 1, dj plus 1. You see, it is like j minus 1 here is index, but here j is index and I have that minus 1 because I connected that vertex n and the degree of this changes by 1 and everything going to dn minus 1 because now I don't have dn anymore. We see Tj and Tj prime. Actually, I can say we see there is a bijection or there is a one-to-one correspondence between Tj and Tj prime. So I can say Tj is equal to Tj prime. Okay, I want to find that number, but actually for this one I have some information because Tj prime is a family of trees with that degree sequence, actually family of spanning trees of kn minus 1 with that degree sequence. So I already know that number by induction hypothesis, that I know the statement, we believe that the statement is true for n minus 1. So I know Tj prime is equal to, I'm writing that here, but I'm going to repeat that there, so don't worry. The statement was n minus 2 factorial. I don't have that formula here anymore, but it was n minus 2 factorial. And now that I have n minus 1 nodes, it becomes n minus 3 factorial. And then in denominator, I had all the degrees minus 1 factorial. So I have again d1 minus 1 factorial, d2 minus 1 factorial, all the way. Don't forget that it is dj minus 2 factorial because it is itself is dj minus 1. So d of j minus 1. So it will be d of j minus 2 factorial all the way to dn minus 1 minus 1 factorial. The first minus 1 is for index, but the second minus 1 is that minus 1 that we use in front of each of these degrees. Okay, so far we know the size of Tj prime, and from that we know the size of Tj. Let's see what we can do. And so Tj is equal to Tj prime equal to n minus 3 factorial times d1 minus 1 factorial, dj minus 2 factorial, dn minus 1 minus 1 factorial. Okay, I want to make it better. So if I multiply that, let me use another color to do that. If I multiply both parts of my fraction by dj minus 1, it is the same as 1, right? So there is no difference if I do that. It doesn't matter actually. So what happens here, I will have n minus 3 factorial times dj minus 1, not factorial, I'm sorry. And here I will have d1 minus 1 factorial, d2 minus 1 factorial, and this times this, you know, dj minus 2 factorial is the multiplication of all numbers from 1 to dj minus 2. So if I multiply dj minus 1 as well, it becomes dj minus 1 factorial all the way to dn minus 1 minus 1 factorial. Yes, so far we are good because it's like I have the same degree sequence, I have a better formula, better denominator now, and now what is the thing that I need to actually prove? Let's see. We want to find the number of all trees, right? It is my goal to find the number of all trees for that spanning tree. So what happens is that it is equal to sigma of tj's when j can be any of those numbers, because you remember what was j? It was the one that was connected to n. So it can be 1 to n minus 1, right? I can have that degree, that vertex n connected to any other ones. So for that arbitrary j, we computed that number using induction hypothesis. Now for finding all of the trees, for that degree sequence, what I need is to compute a sigma, apply a sigma for j equal to 1 to n minus 1, because it covers all the possibilities for what vertex n is connected to. And let's see what is the result. It is j equal 1 to n minus 1, and I'm using the formula n minus 3 factorial dj minus 1 and the denominator. Okay, see what I do is this. I'm going to apply that sigma on dj minus 1 for j equal 1 to n minus 1 and have this. Okay, let's see what happens when I have this sigma. Let me make it like this. Okay. See here, I have sigma of dj is like this. Sigma of dj minus sigma of 1. For 1 to n minus 1, j is equal to 1 to minus 1, j is equal to 1 to n minus 1. This part is the summation of degrees of all my vertices, but not the n. So we know that the summation of degrees is equal to 2n minus 2, but because the degree of n is equal to 1, and I am not considering the degree of the vertex n, the summation is equal to 2n minus 3. And because here I have 1 to n minus 1, that sigma of 1 will be equal to n minus 1. So it is minus n minus 1, which is equal to n minus 2. So this part is equal to n minus 2. So I have n minus 2 times n minus 3 factorial times d1 minus 1 factorial all the way to dn minus 1 factorial. The first thing we see is that here I have n minus 2 times n minus 3 factorial, which actually gives me n minus 2 factorial. So it is n minus 2 factorial. Okay, so far we are so close to our formula. We are good with that n minus 2 factorial. We are good with that denominator, but we need something else. In the formula, we have the n minus 1 factorial as well, right? But what happens if I have that here? Let's see. dn is equal to 1, right? So dn minus 1 is equal to 0, and 0 factorial is equal to 1. So there will be no change if I multiply that denominator by 1, right? So I can easily have that dn minus 1 factorial here. And what we see is that we have the proposition here. Okay, we showed that proposition is correct. But the proposition is saying that for that special degree sequence, d1 to dn, then if I have that, then the number of spanning trees is equal to this. So let's see the number of spanning trees with that degree sequence. But we have different degree sequences. We can have much more, and it is like I need to compute T of Kn here, which is equal to sigma of n minus 2 factorial, actually sigma of T, let me write that in this way, for all the d1 to dn greater than 0 and d1 plus d2 plus dn equal to 2n minus 2. Okay, I know the result for that. I found that in that proposition, right? So I can say it is sigma of, please keep that one in your mind. I'm not going to write that for all the sigmas. So for all of them, I have that condition. So here I will have n minus 2 factorial over d1 minus 1 factorial all the way to dn minus 1 factorial. Is dn minus 1 factorial. Okay, so how can I handle that one? It is the same as I have sigma of n minus 2 factorial with k1 factorial, k2 factorial, kn factorial, which is when I have k1 plus k2 plus kn. You see each of k's is equal to d1 minus 1. So what is the result of here? That k's must be equal to actually is it is equal to n minus 2, and I have k1 and k2 and all kn's greater or equal to 0. Okay, I have this, and we know this summation is equal to 1 plus 1 plus 1 to the power of n minus 2, which is equal to, I have n times here because I have n k's here, which is n to the power of n minus 2. So we see the result for Cayley's theorem by score. Thank you.